Okay, well, welcome back, and let's continue developing differentiation rules. We just talked about the power rule. Now we're going to talk about the sum rule, and we actually introduced the sum rule in the last video. We had a simple function. It looked a little bit different than this, but it was, y, our dependent variable, is equal to ax to the minus 1. So we just wanted to make the point the last time around that having a negative exponent doesn't change the rule. And then we introduced this constant, b. So we have dy dx is equal to, we're just taking the derivative of y. So we've written y over here explicitly. And this idea of the sum rule really boils down to just distributing the derivative operator through the sum or difference, as you have it, of terms. So our first derivative is of the first term, so we have dAx to the minus 1 relative to dx plus dB dx. B is a constant in this case. So we have dAx to the minus 1. This goes to 0, remember? Right? So we don't have to worry about it. It disappears. It's a flat line. It has a slope which is equal to 0. And we're just left with this part of the derivative of this term. So we have dAx to the minus 1. Use the power rule. Bring the minus sign down in front. Minus 1 times ax over here. Reduce the exponent by 1 so that we get ax to the minus 2 power. Excuse me. Okay, so we have the sum rule then in general. If we have y of x is equal to f of x plus g of x, what is dy dx? That's the question. That's the general question. And as we've noted, in a couple examples already, all we're doing is distributing the derivative operator through the sum of terms. So we have a sum. We're differentiating the sum. We distribute the operator dx through the sum f and g, sum of terms f and g, in order to get the derivative. So if we take a simple example like this, we can remove the left and right outside and inside parentheses here and write dy dx simply as the derivative of this sum of terms. And again, just to be repetitive and a little bit redundant, the only new thing that we're learning here is that if you have a sum of terms, you just differentiate each term in the sum. So where y is equal to x squared plus c plus ax to the fourth plus b, and they could be grouped in any manner you have, as long as you follow the basic rules. The derivative then will just be the derivative of this sum of terms. So we have the derivative of the first term, which is x squared, second term, which is a constant, third term. These are two derivatives that we've already done, right? X squared and x to the fourth. We have another constant in here. We've talked about that. And another constant out here. So the first term, apply the power rule. We get 2x. So we're just beginning to use our rules here. And just remembering again that the derivative of a constant is equal to 0. So we know that dc dx, dB dx are both going to be equal to 0. So in the end, differentiation of each of these terms individually, we get dy dx is equal to 2x plus 4ax cubed. These zeros, of course, remove those terms from the expression, we end up with a derivative 2x plus 4ax cubed. So that's basically the sum rule, and if you're dealing with differences, it really doesn't matter. Sums or differences, we just distribute the operator And in this case, we know that the derivative of these two terms goes to 0. We have the derivative of 2x, which we already know. We have a minus sign here, so we just have a 4ax cubed. Just following the general rule. We bring the exponent down. We reduce the exponent 4 by 1 to get x cubed. So here's a couple additional examples. Probably tired of seeing this one. Y is equal to ax squared. The derivative of ax squared is just equal to 2ax. Now if we had something like a little bit more complicated, like y is equal to x to the 2a, we're just looking at power rule now. Well, it's the same sort of thing. We have a little bit more complicated exponent here. We bring that down in front. We reduce the exponent by 1, so we get 2a times x to the 2a minus 1. Here's a little bit more complicated expression. We'll use the power rule to differentiate, but we have something that looks like this. It's hard to apply the rule that we developed to something like this, so we have to transform this into a function which has the independent variable raised to some power. So we rewrite this as x to the minus 8/5. Remember, this is 1 over x to the 8th is x to the minus 8th. This is the 5th root of x to the minus 8, which we've written out here. Y is equal to x to the minus 8/5. We take that derivative, and we just use the rule that we've already developed. Minus 8/5, reduce the exponent by 1. In this case, it's minus 5/5. So 8/5 minus 5/5 gives us minus 13/5. Okay, the sum rule. Another simple expression. We've got our quadratic here, a parabola. We want to differentiate that. We want to figure out what the slope is of this function at an arbitrary value x. So we distribute the derivative operator through each of the terms. We have a derivative of ax squared with respect to dx plus the derivative of bx with respect to x plus the derivative of c with respect to x. And we end up with this derivative being equal to 2ax plus b. Fairly straightforward. So as a last example, if we have something like y is equal to 2ax to the n plus q is a constant, and unless you see q of x or b of x or d of x, we usually assume that these terms are constants. So our dy dx, this derivative of q goes to 0. We have 2ax to the n, so we bring down the exponent 2nax, reduce the exponent by 1, so we have 2nax to the n minus 1. Over here I've got a negative exponent, minus n, so I bring the minus n down. I have 2 minus 2nax to the minus n minus 1. And again, the derivative of here, we don't bother even writing it out now, is 0. We have those two examples. Now on the next one, we're going to look at the chain rule. And the chain rule is, well, we're just looking at x when it becomes a little bit more complicated. When the function y is a function of x, but a more complicated representation of x, and the chain rule becomes useful for differentiating those that additional level of complexity. So the next time we'll talk about the chain rule and find some examples, practice on them, and we'll see you next time.